Namaskara. I am Keshavamurthy. I am from Dr. AIT, Bangalore. I will be teaching the first unit of Basic Electrical Engineering. The portion is with reference to DC circuits. We will cover the basics of DC circuit like Ohm's law, Kirchhoff laws, and the resistances in series parallel, and also look for the application side of it also. So in that respect, as you are aware, energy, every action in the universe requires one or other forms of energy. Electricity is an exceptional type of energy. It can be static or current electricity. Current electricity is the dynamic and is defined as the flow of electrons and is in a closed path. The word current has been derived from currere. It is from the Latin language, and finally it has resulted into current in Middle English. Current is nothing but the movement of charges, and the current, the power or the electricity can be transferred over two wires called the interconnecting wires to any other point. Current electricity or electricity can be used for heating, lighting, chemical, magnetic and mechanical effects. Current electricity or electrical energy is a converted form of energy derived from that available in nature, like fossil fuel means it is oil, coal and natural gas, hydro, nuclear, wind, solar, sea. These are nothing but the naturally available resources, and it can be converted into electrical energy. And conversion of energy from hydro, fossil, nuclear, wind, geothermal, tidal wave to electrical energy is based on the Faraday's laws of electromagnetic induction. Here, the mechanical energy derived from these natural resources will be converted into electrical energy. According to the Faraday's law, whenever there is a relative motion between the flux and the conductor, an EMF is induced, and this EMF will be in a position to drive current through a closed path to do some useful work. In order to get an idea, look at this. Think of a coil. Coil means a wire, copper wire or aluminum wire coiled like this, and connect this one to a galvanometer. As such, galvanometer is a current detecting device. Think of a magnet, permanent magnet. The flux always comes out of the North Pole and enters into the South Pole. The presence of the magnetic field is represented by the lines of force. When both of this is nothing but the field or the magnet. When both of them are stationary, there will not be any deflection in the galvanometer. However, when the magnet is pulled this way, there will be a deflection in the galvanometer, maybe in this direction. So long the magnet is moving, there will be deflection in the galvanometer. Once the magnet comes to standstill, the deflection will be zero. Move the magnet in the opposite direction, you will observe the deflection to be in the opposite direction like this, and persists so long the magnet is moving and comes to zero once the magnet comes to standstill. So with that, instead of this being a galvanometer, let us say it's a lamp. In that case, as the magnet is moved this way or that way, what happens? The mechanical energy supplied to the, as I move this way, it's as good as providing mechanical energy to the magnet and goes converted into electrical energy and available here in the coil. Say, as and when the magnet moves, there will be an induced EMF according to Faraday's law. Whenever there is an induced EMF and the closed path, there will be a current here now. A moving current is always responsible in providing some useful work. In that respect, here the lamp starts glowing, indicating the mechanical energy supplied to the magnet goes converted into electrical energy. Keep the magnet stationary, move the coil this way or that way, the same thing happens. However, the mechanical energy supplied will go converted into electrical energy and available in the coil only and not magnet. Instead of this, a magnet, think of a wood. Move the wood this way or that way, there will not be any, the lamp will not be glowing, indicating that the wood is not responsible in converting the mechanical energy to electrical energy, it is only the magnet. The presence of the field or the flux is responsible, and it acts as a factor to convert mechanical energy to electrical energy. So with that, so this is the coil, this is the coil, this is the lamp, and this is the magnet. As this magnet is moved this way or that way, the lamp starts glowing. Unfortunately, there is some problem. Anyhow, it has been explained here now. The EMF induced in the circuit is proportional to the time rate. That is what I said. The EMF induced will depend upon different factors. It depends upon the magnetic field, the velocity with which the magnet is moving, the position of the coil, orientation of the coil, shape of the coil, all those things also comes into picture. In practice, as such, you cannot move this way or that way and produce electrical energy. To produce energy in terms of megawatt, say generally the coil will be rotated in the magnetic field, or the magnet will be rotated in the magnetic field to generate the power. So in that respect, in practice, large power in the range of hundreds of megawatt is generated by rotating coil or coils driven by prime movers like hydraulic steam or gas turbines in a uniform magnetic field or constant length. The type of induced EMF in this case, when it is rotated in the magnetic field, it is as good as this is the coil. If this is called as A and this is B, this is A and this is B. When it is rotated in a magnetic field, when it is rotated like this, there will be an induced EMF. When this is here, the same thing has been shown here. This is the first position, second position, like that. At this position, the induced EMF in this AB is 0. This is 0 here. As it starts moving, the induced EMF goes on increasing, reaches maximum value, goes on getting reduced, becomes 0 here, and it will change its polarity over here now. In that respect, the EMF induced will be sinusoidal in nature like this. When the voltage is alternating, the current is also alternating, and as the alternating means the charges will be flowing in both the directions. Over half cycle it flows in one direction, in the other half cycle it flows in the other direction. However, the electricity need not only be the AC, it can be DC also. Certain application calls for only DC. In that respect, DC is required for the battery charging and for electrolysis, and also most of the electronic devices functions only on DC. On the other, say as it is difficult to transfer DC over long distances, generally the generation will not be DC, but it is AC. Because of transformer, the power can be transferred easily from one point to another point at high efficiency. Here you can see, while this is AC, the current, say the charges flows in one direction in this positive half cycle, and during the negative half cycle it flows in the other direction. On the other hand, in case of the DC, the current remains to be in the only one direction, or voltage remains to be in only one direction, it will not change its polarity, or you can say it is time invariant while AC is time variant. When it comes to the DCs, it can be obtained from batteries, solar cells, thermocouples, fuel cells are the source of DC power. It can also be obtained from DC generator, where whenever you come across a rotating coil, there will always be induced EMF of alternating nature. It can be converted into DC by going for commutator and brush arrangement or using a rectifier. When it comes to electric circuit, an electric circuit is essentially a conduit that facilitates the transfer of charge from one point to another point. The charges in motion transfer energy from the point of origin, say a battery, to utilization, say a lamp. In that respect, a lamp converts electricity to light. Electric circuits, simplex or complex, can be described in different ways. It can be described through verbal description as it does not provide a quicker mental picture of the actual circuit. It is seldom used. It can be other ways also: block diagrams, pictorial diagrams, and schematic diagrams. Block diagrams use interconnected blocks to describe their relationship to each other in a circuit in simplified form. Each block is labeled to indicate what they do or what they contain. The figure shows the block diagram of a simple flashlight, where, say, this is the energy source. As you are aware, a flash light contains the cells, a lamp, and a switch, and all these are connected through connecting wires, and that has been shown here by the block diagram. This is the energy source, that is nothing but the dry cells. Then the transmission path are the connecting wires. The switch is indicated by the control block, and the lamp or the bulb is indicated by the load. And it may be a pictorial diagram, wherein which the diagram is indicated by going for component which looks like in practice. So in that respect, you can see here now, this is the battery, this is switch, and this is the lamp. But it is too cumbersome to go for this pictorial view or even say the block diagram. In that respect, schematic or circuit diagrams are used, where the standard symbols are used to represent the different components of the circuit. In that respect, you can see here now the same flash light has been shown by this schematic diagram, where the battery or the cells have been shown by this, switch is shown this way, and this is the lamp. So, as such, the lamp converts the heat electrical energy into light energy, wherein which the light comes from a resistor. So in that case, the lamp is generally indicated by the resistor, that is nothing but this one. So generally, this is much used as the electric circuit diagram. Then when it comes to the different parameters of the electrical circuit, it is voltage, current, and resistance. Voltage refers to an energy source, and it is the ability to produce current within a closed loop. An electrical load consumes, so of course, the voltage will be driving current into the load, or it may be loads. What's a load? Load is nothing but a device which converts electrical energy into some useful energy. In that respect, lamps converts electrical energy into the light energy, and similarly the electrical appliances are also the loads. What's the definition of the voltage? It is the work done per unit charge. So in that case, voltage can be taken as W by Q, W being the joules, the work done is the unit is joule, and the charge is nothing but coulomb. Therefore, J by C is the unit of voltage. However, it is not always used as J by C only. It will be generally represented by volt, which may be small v or capital V. Small v is a time variant representation, while capital V is time invariant. The voltage is described both in magnitude and direction. The voltage magnitude may be in microvolt, millivolt, or say kV. The electrical signals that you come across in say bodies or say communication signals, it will be in millivolt, while the voltage of transmission may be in kV. Often it will be represented in volt also, like for domestic purpose, 230 volts is being used. The voltage source is represented by these symbols. This is the DC source, where the longer side line represents the positive terminal of the source, and this is the negative source. However, instead of going for plus and minus sign or plus sign anode, the arrow is used where the head indicates the positive terminal of the source. Say here, sometimes the voltage source is also represented like this, or this is also a DC source, while AC source is shown by showing an AC symbol inside a circular block. Voltage is also called as electromotive force, that is nothing but EMF, or potential, and sometimes the pressure or tension is also used. In that respect, you must have come across high tension wires indicating high voltage wires. As the voltage is defined between 2 points, voltage is also called the potential difference. In order to represent the voltage between two designated points, double script notation can be used, in which case we can have an idea with reference to this. Consider 2 points A and B. If this is at higher potential and this is at lower potential, or if this is taken as the reference, the voltage between these two can be represented as VAB, indicating A is at higher potential with respect to B. Obviously, you can write VAB is equal to minus of VBA. Like what is done in vector calculus, the same thing can also be applied here. When it comes to current, under the influence of electric force or the voltage, the charges move in the circuit. Moving electrons is recognized by the term electric current, as you are aware. The symbol I, small I or capital I is used, I or I, while this is time variant, this is time invariant. And then the intensity or the magnitude of the current is represented by the ampere, and is also defined as the movement of charges across a section in particular time, or per second you can say. So, in that respect, current is nothing but charge divided by time, and that is generally denoted as I is equal to Q by T coulombs per second. Alternately, it is the time rate of charge. So, in that case you can represent I as equal to dq by dt also. The current is described by magnitude and direction. The unit of current is ampere and the symbol is A, and often you come across AMP or AMP also. They are not official way of representing the current or ampere. Even 10 ampere is not also acceptable, as starting from capital A indicates the name of a person and not the unit. The magnitude of the current can be in nanoampere, microampere, milliampere, ampere or kiloampere, like that. And the direction is represented by an arrow. The arrowhead will indicate the direction in which the current is flowing, and as such, if you have 2 points A and B, if the current is flowing this way, obviously the direction of the current can be indicated as IAB, where A represents a higher potential compared to B. So, the current is flowing from A to B. Obviously, we can write this as equal to minus of IBA. What we can learn later, I will just give the characteristic of the current also. The current always flows from higher potential to lower potential, and at the same time current always takes the least resistance path that we will see at a later stage. Resistance is the opposition to flow of current, and resistor is a component of a circuit. The symbol used for the resistance is this one, which can be represented by small r or capital R as the case. The resistance, the unit of resistance is ohm, and it can be calculated by this expression R is equal to rho L by A, where rho is nothing but the resistivity, L is the length over which the current is flowing, A is the area over which current is flowing. Rho is the resistivity, and it can be, unit of this one can be ohm centimeter. As such, R is equal to rho L by A, and often the rho will also be expressed in other ways also. To understand that, consider this is nothing but RA by L. If this is ohm, area is in centimeter square, length is in centimeter, that leads to ohm centimeter. That is what has been shown here. However, many a times area involved is less, length involved is large. In that respect, this is represented as rho is equal to R by L by A. This will be equal to ohm by length is represented in meter and area is represented in millimeter. In that respect, it can also be represented as ohm per meter per millimeter square. And for copper, it can be taken to be equal to 0.021 at about 75 degrees centigrade. And when it comes to resistivity, lesser the value of resistivity, the conductivity is more. That means the opposition offered will be less. Though this expression does not indicate or include the term representing the temperature, this resistance depends upon the temperature. As the temperature increases, the resistance also increases in case of metals and decreases as the temperature decreases. Knowing the resistivity and the resistance at a particular temperature, the resistance at any other temperature can be calculated by this expression, where R2 is equal to, this is R1 into 1 plus, you can see here now, 1 plus alpha 1 T2 minus T1. The reciprocal of the resistance is called the conductance. Unit is mho, or it is also taken as S, the Siemens. So with that, having known the basic parameters of the DC circuits, we will go for the Ohm's law, Kirchhoff law and other things. So in that respect, after completing this chapter, students should be able to understand the basic concepts in circuits, solve for unknown quantities like resistance, current, voltage, power in series, parallel and series parallel circuits, examine the applications of circuits. When it comes to Ohm's law, it relates the resistance, voltage and current. Say according to the Ohm's law, at constant temperature, the resistance remaining constant, the current is directly proportional to the EMF impressed into the circuit and inversely proportional to the resistance of the circuit. It is as good as I is proportional to V, or I is equal to V by R, where the constant of proportionality is 1 by R. It can be written, this is Ohm's law, it can also be expressed as IR, or it can be taken as V by R. Say Ohm's law can be expressed in any one of these possible way. When it comes to the energy is the ability to work, or capacity to do work, and work is nothing but transferring of energy from one form to another. So that means work done means it is actually some sort of energy has been converted to another sort of energy. Therefore, work is done each time energy changes from one form to another form. A load which receives electrical energy from an energy source does work to convert into different forms. In that respect, electric lamp converts electrical energy into light energy, electric stove converts electrical energy into heat energy, electric motor converts electrical energy into mechanical energy, electric fan converts electrical energy into wind energy, speaker converts electrical energy into sound energy, and similarly the electrolysis involves in converting electrical energy to chemical energy. What is the expression for the energy or the work done? As such, the voltage is defined as equal to work done per charge, that is nothing but this, that is nothing but the Q. So therefore, the work done W is equal to V into Q. As such, Q is nothing but equal to I is equal to Q by C. Therefore, Q can be written as equal to VI T. Current is nothing but Q by T. Therefore, W is equal to V into Q. Q is replaced by IT. According to Ohm's law, we know this V is equal to I also, IR into IT. That comes to I square RT. Or it can also be taken as I is equal to V by R into T. This will be V square by RT. The energy can be calculated or expressed in any one of these terms, and the unit is nothing but the joule. Say the joule is written as this way and denoted by capital letter. Joule is also watt second. That way. When it comes to power, it refers to rate of at which work is done. So, rate at which work done means power will be equal to the energy divided by the time. This will be equal to VIT or I square RT, or it may be V square by RT divided by T. With that it works out to be VI, or it may be I square R, or it may be V square by R. The unit is nothing but the watt or indicated by W. So, in that respect you can see the amount of power depends upon the device also. For example, a flashlight consumes more energy than an electronic watch. Say if you use cells, the energy stored in the cells will be drained very fast when a flashlight is used. It is not so when an electronic watch is used. The unit of power is watt, that is what I said. Joules are joules per second and is symbolically represented by capital W. When power is large, it is generally expressed in kilowatt or it is expressed in megawatt. In any circuit, power supplied by the source or sources must always be equal to the power dissipated. It is nothing but conservation of energy, where the power supplied must always be equal to power consumed. In practice, all the components in the DC circuit, including the connecting wires, consume power. While the power dissipated in the load is useful, the power dissipated in the connecting wires or other connected devices is a loss, or it represents a loss in the circuit. Every practical device has its own limitation also, in the sense they cannot withstand higher temperature. For example, a resistance cannot be subjected to an indefinite temperature. As the power consumed by the resistor goes on increasing, instead of consumed, received, input, power consumed by the resistor, power received by the resistor, or power input to the resistor is more and more. What happens? The heat developed in the resistor also goes on increasing. If the heat developed is more, the heat will destroy the resistor. Therefore, they are to be operated within certain limit only. In that case, every resistor will have its own what is called as power rating, or the maximum power that it can withstand. The maximum power that can be calculated from this expression also, maximum voltage that may be applied to the resistor is calculated by this expression. V is equal to, this is power is equal to V square by R. Therefore, the maximum voltage that can be applied will be equal to this. And similarly, you can find out what is the maximum current it can withstand also. As such, P is equal to VI. We can calculate I is equal to P by V also. The resistors must be ensured to see that it is not getting damaged. When it comes to practical unit, what is that? Practical unit of energy. In that respect, joule being a very small unit, so it becomes difficult to use it for measurement of large energy. As an example, energy required to raise the temperature of 1 liter of water to boil from 50 degrees centigrade is 355,410.5 joules. So, that is nothing but 3,55,410.5 joules. It becomes difficult to represent always. to overcome this one, generally the kilowatt hour is used, in which case you can see here now 1 kilowatt hour is nothing but 1000 into 3600, that comes to 3.6 into 10 to the power 6 joules or watt second. So in that respect, the joules that was required to heat the to bring the water to the boiling level can be represented as 0.1 kilowatt hour. Instead of 3,55,410.5 joules, it can be represented as 0.1 kilowatt hour. In that respect, all electricity distribution companies use kilowatt hour as the basis to charge the electricity bill. Instead of calling it as kilowatt hour, they generally call it as a unit. And energy is measured by using the energy meter or watt hour meter. When it comes to voltage sources, it can be an independent voltage source or it can be dependent voltage source. An independent voltage source is one whose output is unaffected by any other parameters of the circuit, while a dependent voltage source, the voltage depends upon the other variables in the circuit. Say the voltage will be decided by the variation at any other point of the circuit also. Further, independent voltage sources can be classified as ideal and practical, or practical is also called as the real sources. When it comes to ideal source, this is an ideal source, DC source, where there is no loss inside this battery. No loss inside means no resistance inside. The loss can be represented in terms of a resistor also. No loss means no resistor inside, or no resistance is offered by the battery inside this. Our internal resistance is 0. An ideal voltage source is assumed to have no internal loss of energy and hence no internal resistance. Hence, the voltage at the terminals remains the same irrespective of the current supplied by it. However, every practical voltage source will have some internal loss and therefore will not maintain a constant voltage at all loads. Thus, this effect is generally considered in terms of an internal resistance or source resistance. In that respect, the source resistance is indicated to be in series with the voltage source. That is what you can see here now. This is the voltage source and this is the internal resistance. This voltage will always be less than this voltage because of a drop that takes place here now. When nothing is mentioned, generally the voltage sources are taken to be ideal sources. Energy sources can provide constant voltage so long they are powered with an input. And for example, a continuously powered generator can supply power maintaining constant voltage. However, a battery cannot maintain a constant voltage over time, meaning that the voltage will drop as the battery is used at its terminals because of the losses, its storage energy or the loss of charge. However, for most of the purposes, the voltage can assume to be remaining constant to work out the problems. You come across different terminologies also. It can be supply voltage, applied voltage or open circuit voltage. The voltage across a source that's across a battery, say, when not connected to an external circuit is called the electromotive force, supply voltage, applied voltage, source voltage or open circuit voltage. These are the two terminals of the battery. I will call it as AB. When it is not connected to an external source, if this is say V is equal to 10 and this is some resistance, if a voltmeter of very high resistance is connected, this records 10 volts. However, when it is connected to a resistance, the voltage recorded by this will be less than the drop that it takes place. That is what it means. The voltage across a source when not connected to an external circuit that is when the current driven by the source is 0 is called the electromotive force, that is EMF, supply voltage or applied voltage, source voltage or open circuit voltage. In an ideal case, this is the voltage applied to a circuit connected to the source. Then others are load voltage. Voltage across the load is called the load voltage. Then you come across voltage drop and voltage rise. Voltage across a component in a circuit is often called voltage drop when current flows from higher potential point to a lower potential point in the circuit. Voltage rise is taken when the voltage is traced from negative terminal to positive terminal. Assumptions in solving problems. The connecting wires are assumed to have 0 resistance. Therefore, the voltage drop in them is 0. In other words, all the points on the connecting wires are at the same potential. Also, there will not be any loss in the connecting wires. However, in practice, all these ideal cases are not met. Then, when it comes to circuit analysis, what is circuit analysis? Circuit or network analysis is the mathematical process, and its goal is to determine the voltage across and the current through every component in the circuit planned for a specific purpose. As the circuit becomes more complex, that means the resistances are connected in different configurations, it is not possible to find out the current and voltage using Ohm's law alone. In that respect, the Kirchhoff law comes into picture or can be used. There are two laws. One is the current law and the voltage law. According to the first law or the current law, the algebraic sum of the currents at any junction is 0. So, in that respect, this is a circuit where O is nothing but the junction or O is the node, and here the some currents are flowing into the junction and some currents are going out of the junctions. The current flowing into the junction can be taken as positive and going out can be taken as negative. However, this is only a convention, therefore, it can be assumed in the opposite direction also. If at all we take the current flowing into the junction as positive, then this is I1 minus I1 plus I2 minus I3 plus I4 plus I5 must be equal to 0. That is what has been written here. Minus I1, that is this one, as the current is going out. I2 is into the junction, that is plus. I3 is going out, therefore it is minus. I4, this I3 is going out, it is minus. I4 is into the junction, that is plus. I5 is also plus. It can be represented as symbolically sigma IN equal to 0. According to Kirchhoff's second law, it is the algebraic sum of the voltages around a closed loop is equal to 0 at every instant of time. Or it can be stated the algebraic sum of the voltage rises must be equal to algebraic sum of the voltage drops at every instant of time. A closed loop, what is a closed loop? A closed loop or a closed circuit is a conducting path in a circuit that has the same starting and ending points. If the current flowing through a circuit returns to the same point from any other point, the circuit is said to be a closed loop. While tracing the loop, voltage encountered may be the voltage of the sources or voltage drop across the resistances. While writing the KVL equations, the following sign conventions can be used. If the voltage of the source is traced from negative to positive terminal, if the source voltage is traced from negative to positive, the voltage can be taken as positive. And when you are tracing the drop across a resistor in the direction of the current, that is from plus to minus, the voltage drop can be taken as negative. However, there are conventions to go for the other way also, but we will go for this one. Tracing from negative to positive of a voltage source is taken as plus V. Going from, if this is R and this is I, tracing the drop across a resistor in the direction of the current is taken as plus IR. This is plus to minus means minus IR, that way. The sign conventions need not be the same, as I said. It can be opposite to what has been stated under A and B. The choice of starting point is totally arbitrary. You can start tracing the circuit from any point of your choice. So, with these things in mind, going for the application of Kirchhoff's second law for this loop, it is minus to plus, that is nothing but plus E1. Then the drop across this has been taken as V1. According to Ohm's law, drop across this will be I into R1, where I is the current in this loop. Therefore, since we are going from plus to minus, the drop is taken as minus, that is minus V1, and this will be minus to plus means it is plus E2. Here the drop is V2, plus to minus, that is minus, and here plus to minus, which is in the direction of the current, therefore it is minus V3 is equal to 0. The same thing can also be written as equal to E1 plus E2 is equal to IR1 plus IR2 plus IR3, in the sense the voltage rise is equal to the voltage drop. In general, it can be written as KVL can also be written as sigma Vn is equal to sigma IR or sigma Vn is equal to 0. The resistances can be connected in series, parallel or series parallel. Each configuration has its own applications. We will come to that. The resistances are said to be in series when the current flowing through one resistor also flows to the other resistor. In that respect, you can see here R1 and R2 are connected in series across the voltage source V. According to Ohm's law, V1 is the drop across this R1 is nothing but the current is common to both the resistances in series circuit. The V1 is nothing but I into R1, while V2 is equal to I into R2. According to Kirchhoff's law, V must be equal to V1 plus V2. That comes to V1 plus V2, IR1 plus IR2, I into R1 plus R2 leads to I into R12, where R12 is nothing but the equivalent resistance or total resistance offered to the source. Therefore, Kirchhoff's law can be used to reduce the circuit to a simple circuit also. In general, the total resistance, equivalent resistance will be equal to the sum of all the resistances in series, and that will be equal to V by R. The total resistance will always be greater than the largest value of the resistance in series in the circuit. It is clear that KVL helps to replace all the resistors with an equivalent resistance and offers general rule to find the equivalent resistance of a series circuit. Equivalent resistance of a series circuit is the sum of all the resistance and will always be larger than the largest resistance in the circuit. And what will be the power consumed in each resistor? To understand that, we can just look at this. This is V, this is V1, this is V2, R1, R2, and this is I. Power is equal to, it can be taken as V1 into I, or it can be equal to V1 square by R1, or it may be I1 square into I square into R1. Similarly, this is the power consumed by this resistor. P2 can be taken as equal to V2I, or it may be V2 square by R2, or it may be I square into R2. This is the power consumed by each of the resistor. What will be the total power? In that respect, P will be equal to P1 plus P2. This will be equal to VI1 plus VI2 V1I and V2I. So, this will be equal to I into V1 plus V2. This is nothing but equal to Vi. That is one thing. Or it can also be written as equal to, this P will be equal to V square by R12, where R12 is the total resistance and will be equal to R1 plus R2. It can also be calculated by the other way. It is nothing but I square into R12 will give you the same total power. As you can observe here, as the voltage goes on increasing for a given values of resistor, the current also goes on increasing, the heat developed in them also goes on increasing, which may lead to destroying of the resistor. That way. Applications of series circuit. Series step topology can be used as a voltage divider to limit the current in a circuit, or it can be to limit the current in a circuit. Voltage divider can be a fixed voltage divider, or it can be variable voltage divider. A fixed voltage divider is something like this. If this is the voltage applied, let us say it is something like say 100 volts, you can go for drop it for 60 and you can get 40 volts also here now. So, this is nothing but a fixed voltage divider, and variable voltage divider will be this way. The voltage can be obtained here. When it is here, the voltage level will be 0. When this is here, it is 100 volts. In between, the voltage is obviously between 0 and 100. So, in that case, when the resistor is used as a variable resistor to get the output, it is generally called as a potentiometer, or it is also called as pot. So, this is the fixed voltage divider used to bias a transistor here, while the variable divider has been considered here, where this is the speaker and this is the amplifier, and this is nothing but the pot variable one, that is not this one. So, it can be moved upward or it can be moved downward. So, in that case, when it comes downward, the applied voltage to this amplifier will be less, therefore, the output is also less, the speaker output is also less. As it goes this way, the output of the speaker is more because the input to the speaker is more because of this higher voltage applied to the amplifier. Resistance when connected in parallel. When two resistances are connected such that there is a division of current with the same voltage existing across that, the resistors are said to be in parallel. Here you can see the two resistors are in parallel, these two are parallel across this. According to, you will observe the voltage common to both. The current in this one according to Ohm's law will be equal to V divided by R1. Similarly, the current here will be V divided by R2. Since the current that is coming out of the battery divides itself here now, some current goes this way, some current goes this way, application of Kirchhoff's Ampere law at this point leads to I is equal to I1 plus I2. So, that is nothing but this, which is V by R1 V plus V by R2. When it is simplified, it comes to V by R12, where R12 is the equivalent resistance and can be taken as R1 R2 over R1 plus R2. So, this R12 can be calculated by is the total resistance offered to the source and can be calculated by this total voltage applied to the circuit and the total current supplied by the circuit. And here again the power can be calculated by the same expressions as we discussed in the series circuit, where the relevant values are to be used. The power consumed by the first branch is nothing but I1 square into R1, or it is VI1, or it may be V square by R1, while in the second one it is I2 square R2, VI2 or V square by R2, like that it goes. The total power can also be calculated by this I square R12 or VI or V square by R12. As the number of resistances goes on increasing in parallel, as the number of circuit goes on increasing in parallel, the voltage across them in an ideal voltage source remains the same, but current supplied goes on increasing. So this this property has been utilized in distribution system, where you come across all the appliances at home connected in parallel. So when it comes to the current divider rule, the current divider rule offers a shortcut or a shortcut approach to find the individual branch current without knowing the voltage. How it can be? In that respect, if this is R1 and this is R2, I1, this is I2, this is the total current I, voltage. I1 is nothing but V by R1, but V is nothing but equal to I into R1 R2 over R1 R2 divided by R1. With that, R1 gets cancelled, you will be left with, this is I1, this will be I R2 over R1 plus R2. That means the current in this branch is the total current here multiplied by the resistance of the opposite branch divided by the sum of the two resistances. In the same way here, the value of I2 will be equal to the total current I into resistance of the opposite branch R1 divided by R1 plus the sum of the two resistances R1 and R2. The next one is nothing but the resistances in series and parallel. These circuits, the circuits that you come across in, say, receivers, radio receivers or television sets and others, they will be the combination of series and parallel circuit, and the rules that are meant for reducing the circuit into a simple circuit used in case of series and parallel can be used for this also. In that respect, here you see a series parallel circuit. This is a series resistance and these two are in parallel. These two can be combined to have one resistance. That is nothing but R2 and R3 can be replaced by R2 R3 divided by R2 plus R3, and the total resistance will be R1 plus R2, R1, that is this one, plus R2 R3 divided by R1 plus R2. The current supplied will be equal to the total voltage divided by R equivalent, and the voltage V1 is I into R1, and then the power consumed by R1 will be equal to I square into R1 or V1I or V1 square R1, and from current divider theorem I2 can be written as equal to I2 into R3 over R2 plus R3, and from which you can find out the power in individual resistances. Analysis of circuit using multiple number of loops. So when the circuit are not connected in series or parallel, what happens? In that respect, these two are in series across a voltage source, and these two are in parallel across this. However, when you have a circuit supplied by two sources and the resistance is connected in this way, they are not in, neither in series nor in parallel, they are in actually what's called as T configuration. In that respect, how to find out the current in this? The network reduction technique cannot be applied as it was done in this case, so therefore the Ohm's law cannot be directly considered here. In that respect, we will have to go for the equations based on Kirchhoff law as well as the Kirchhoff's current law and Kirchhoff's voltage law to solve this. In that respect, we come across what's called as the loop current method and branch current method that we will discuss in the next class.